Now there are certain examples based on the nuclear fusion. In nuclear fusion process, 4 hydrogen atoms combine to form a helium atom with 2 positrons. Now we have to calculate the energy released in the process. The basic principle will be that we write a reaction, then we will consider the masses of reactants and the masses of products. We will find that if the masses are accurately considered up to at least 3 places of decimal or the 6 places of decimal, the mass of reactant will be slightly greater as compared to the mass of product. And the difference is called the mass defect, and that mass defect gives rise to energy. That is what the principle of most of the questions in nuclear fusion. So solution is like this. Initial mass we have calculated. 4 hydrogen atom means each atom has mass 1 AMU and up to 3 places it is 1.007825 multiplied by 4. Then we will calculate it by multiplying this number. Total final mass, that is 4.0037, and we will find that decrease in mass will be given by the difference of the two. Now this difference is given as 0.026598 AMU, and we know that 1 AMU in approximation is 931 million electron volts. So whatever number is given in AMU, that is multiplied by 931, and the net energy will be 25.69. Like in the numerical example, we are finding that 4.003 is mentioned and 4.031. It means that reactant side has mass less, product side has more, and this is called absorption of energy. So mass must be negative, but it is a scalar, so we have not taken the negative sign. Now there are important points to remember. The discovery of nucleus, that is due to Rutherford. Rutherford discovered nucleus during alpha scattering experiment. Neutron was discovered by Chadwick, that is during disintegration of 4Be9 by alpha particles. Packing fraction, that is mass defect over nucleon number, is called the packing fraction. Nuclear with negative packing fraction is more stable. Greater the binding energy per nucleon, greater will be the stability. This is explained in the binding energy curve. That is, binding energy per nucleon is normally 8 to 8.8, and if it is less than 8, then instability takes place, and the peak value of binding energy per nucleon is for iron, and that is 8.8. Nuclear fission was discovered by Otto and Strassmann. Nuclear forces are the strongest known forces in nature. This we have discussed in the concept of nuclear forces, that nuclear forces are charge independent and spin dependent. Other thing important is that nuclear forces are stronger as compared to electrical forces. Electrical forces are stronger than gravitational forces. Gravitational force exists in all the pairs of nucleons, that is pp pair, nn pair, and pn pair, but electrical forces has more probability among the proton pairs. We have also discussed earlier that nuclear forces are stronger than electrical forces by 35 to 100 times, and nuclear forces are stronger than gravitational forces by 10 to the power 34 to 10 to the power 39 times. The relative strength of the gravitational, coulomb, and nuclear forces, that is I have already explained, and that is mentioned from gravitational towards nuclear force. 1 is to 10 to the power 35 is to 10 to the power 36. The high density of nucleus suggests that nucleus is compact. The first nuclear reactor was made by Fermi. Neutron having energy 0.03 are called thermal neutrons. However, the energy is not fixed, it varies. Critical mass of uranium is generally 10 kg. This is a very necessary condition for carrying out nuclear fission. The nuclear reactor is based on the controlled chain reaction, because if it is uncontrolled, then there will be destruction process, And for controlled chain reaction, we find it will be very useful in the production of electrical power. The nuclear forces between the protons, the two neutrons, and one proton have the same magnitude. So pp forces, the nn forces, and the pn forces have equal magnitudes. Fusion takes place at high temperature, 10 to the power 7 degrees, maximum 10 to the power 8 degrees. Fusion of nuclei is an uncontrolled process. There is no reactor made for the fusion process. Density of nuclei of all atoms is same, that is of the order of 10 to the power 17 kilograms per meter cube, and normally it is found to be 2.4 10 to the power 17 kilograms per meter cube. The actual discovery of pi mesons was first made from the study of cosmic radiations. Well, I will give more light to the mesons. You can remember that meson particles were first discovered by a Japanese scientist, Yukawa, in the analysis of cosmic rays. And normally we go through with positive meson, pi plus, negative meson, pi minus, and neutral meson, pi naught. The family of mesons is called pions. The mass of positive and negative meson is generally 208 times the mass of electron, and for neutral meson it varies from 264 times the mass of electron to 273 times the mass of electron. The positive and negative mesons are antiparticles of each other. When they interact, there will be formation of a photon of gamma rays. Neutron is neutral and the spin angular momentum is half h over 2 pi, that is h over 4 pi. Now, more elaborately, we can also use a plus minus sign also. The plus sign with half h by 2 pi means clockwise spin, and minus will indicate that is anti-clockwise spin. Escape of neutrons is proportional to r square. R stands for the radius of nucleus, and the order of the square of radius is 10 to the power minus 30 meters square. The fusion process is two hydrogen nuclei fused together, forming that is 2He4 along with neutron. So it is a helium nucleus with a neutron and 3.27 MeV of energy. Or we can say that this reaction is 2He2 along with two neutrons. So N means we have more number of neutrons if we make it as helium-2. 1H2 and 1H3, this is another fusion. This is called deuterium-tritium fusion. It gives rise to 2He4 along with neutron and 17.59 million electron volts of energy. All reactions obey the law of conservation of charge and mass. Bethe was awarded Nobel Prize for his work in nuclear fusion related to fusion reaction. To achieve fusion in lab, a tokamak is used. It is a device to confine plasma. That is collection of deuterium, tritium nuclei in this case. Well, more elaborately, plasma is fourth state of matter. It is highly ionized state of matter, net charge positive, deflected by electric and magnetic field, and it is highly compressed. So in the photosphere, plasma state is responsible for the formation of high temperature 10 to the power 7 to 10 to the power 8 degrees centigrade. So this process is achieved in lab in a tokamak. Research atomic reactions. Well, research atomic reactions, they are normally Apsara reactor. It was made in Bombay, so it is installed in Trombay. This is 1 megawatt reactor, means it can generate power equivalent to 1 megawatt, that is 10 to the power 6 watts, and was made in Bombay. An alloy of uranium and aluminium is used as fuel, and this is also known as swimming pool type reactor. We can have more idea about these reactors when we will proceed in the advanced study. Now, Soyuz reactor, this is another one, and it is constructed with the collaboration of Canada and it is of the value of 40 megawatt. That is 40 multiplied by 10 to the power 6 watts of electricity is generated inside rooms. And this is also used for the production of radioisotopes, which are used in medicine, agriculture, and industry.